Now that we've reviewed the concept of concentration, the amount of solute dissolved in solvent, and we've revisited stoichiometry, we can kind of combine those skills together to complete solution stoichiometry. When we have aqueous solutions, how can we apply knowledges of our knowledge of grams, moles, atoms, molecules, particles, volume together, and to do some chemical analysis? What that basically means is a fancy way of saying doing a lab. And how can we analyze the data? So the most common way we'll do this with solutions is by thinking about titrations. So here's a picture of a titration. You have a burette filled with a base that you know the concentration of, like sodium hydroxide or lithium hydroxide, something like that. And then you have a flask filled with an acid, but you don't know the concentration of the acid. And your goal is to figure out what is the exact concentration of that acid. Well, you're going to do a titration. You're going to slowly add base, okay, until you get to a point when this solution turns pink and just barely faintly stays pink. We know it turns pink because you have phenolphthalein indicator in there, which turns pink in the presence of a base. And once it's turned just faintly pink, you've reached something called the equivalence point, which I'm just going to abbreviate, the equivalence point. And what's going on at the equivalence point? Well, at the equivalence point, the moles of H plus equal the moles of OH minus. This is when we mix a strong acid with a strong base. The moles of hydrogen ion equal the moles of hydroxide ion. Basically, what's going on at this point is this means for every one hydrogen ion you have, there's another hydroxide ion floating around. So all hydrogen ions and hydroxide ions are basically going to pair up. They're going to react, and they're going to get together to form water. So there's no hydrogen ions floating around, so the solution won't be acidic at all. There's no hydroxide ions floating around, so the solution won't be basic at all. So if you're ever mixing a strong acid with a strong base, and you reach the equivalence point, you know that the pH equals 7. Now, we'll get to what happens if you don't have a strong acid and a strong base, but for now, we just need to use that concept. So, let's go to a problem. Number one says, how many grams of calcium hydroxide are needed to neutralize 25 milliliters of 1.1 molar nitric acid? Let's just, a little typo, we'll keep this with lithium hydroxide, so the formula would be LiOH. Nitric acid, this is a habit you need to get into if you're given just the name of the compound, rewrite the formula. And think about what's it asking for. It's asking for how many grams are needed to neutralize 25 milliliters of 0.1 molar nitric acid. So, our eventual endpoint, we got to figure out grams. So if we work backwards from grams of lithium hydroxide, we'll need to know the moles of lithium hydroxide. If we know the moles of lithium hydroxide, we need to know the moles of nitric acid. Well, how do we do that? This is your key word, neutralize. If you're at the neutralization, if you're doing a neutralization, that means you've reached the equivalence point. When the the moles of hydroxide are equal to the moles of hydrogen ion. They are equivalent, they are equal. So since that is true, we know that the moles of hydroxide will equal the moles of hydrogen ion. So if we can figure out the moles of hydrogen ion, we can go and follow those 3 steps to get the lithium hydroxide, the mass of lithium hydroxide. So how do we do that? Well, we know that we have 0.1 molar. We know molarity is equal to the moles over liters. Well, I have 25 milliliters, so that's 0.025 liters. So we solve for x. This gives me an answer of 0.0025 moles of nitric acid. Now, since we have 1 hydrogen for every 1 molecule of nitric acid, because the subscript for H is 1, the 0.0025 moles of acid is the same thing as the 0.0025 moles of H+. Now, if there was a 2 there, that would change something. If there were 3 protons, that would change something. But for now, since that's the moles of H+, we know at the equivalence point, that has to also be equal to the moles of base. since there's one hydroxide for every one molecule of lithium, because the subscript on OH is 1, we know that this is also equal to the moles of hydroxide. So now all we have to do is if we take 0.0025 moles of hydroxide, we just got to convert that to grams as our last step. 1 mole, mass of lithium hydroxide is 24 grams. So if we do that math out, we get an answer of 0.06, but we need 3 sig figs, 00 grams. Boom. So what I don't want you to do is just to memorize, this is how I solve this type of problem, that kind of mental think aloud that I was doing of figuring out my unknown is grams and how to get there. What I need to figure out to get there is the critical thinking part, and that's what we need practice with. So let's go ahead and look at problem number 2. Problem 2 says you find an unlabeled bottle of sodium hydroxide in the fume hood in class. Uh-oh, Mr. Shar got lazy, he got tired, it was 8 o'clock at night, so he left school, and he forgot to label this bottle. Luckily, you're an AP Chem, so you can figure out exactly what the concentration of that sodium hydroxide is by doing a titration. So you conduct a titration in order to identify the concentration of the bottle by adding 50 milliliters of 0.2 molar hydrochloric acid to neutralize buzzword equivalence point 20 milliliters of sodium hydroxide, NaOH. And this problem is asking for the concentration of the sodium hydroxide, that bottle that I left in the fume hood. Well, in order to figure out the concentration, that's the molarity. I know molarity is equal to moles over volume, so I need the moles and the volume. Well, I have the volume is 20 milliliters, so now all I need to figure out is the number of moles. Well, to figure out the moles of base, at the equivalence point, I know that's equal to the moles of acid. So if I can figure out the moles of acid, I'm good to go. So can I do that? Well, you have 0.2 molar acid equals some number of moles over 0.050 liters. So X, you multiply these out, gives you 0.01 moles of acid, HCl. Again, since this is a 1 ratio of hydrogen, there's 1 hydrogen ion for every molecule of HCl. This is also equal to the moles of H+, which at the equivalence point is equal to the moles of base. And since the ratio of hydroxide to sodium hydroxide is 1 to 1, because of the subscript 1 out here, this is also equal to the moles of OH-. So now to figure out the concentration, the molarity, I know that I need the moles, which I have, 0.01, divided by the volume, which is 20 milliliters. But molarity is moles divided by liters, so I got to convert this to liters by dividing by 1,000. I set that up, do the math. The final answer, 0.5 molar. 1 sig fig because of the 1 sig fig here. Look at that. You didn't know what the concentration of this was. Now you can figure it out exactly. Pretty cool. The last concept we need to talk about is dilution. So dilution, if you dilute a solution, what are you doing? You are decreasing its concentration. You are making it less concentrated. You're decreasing the molarity. And the way we usually do that is by taking a stock solution, okay, the word stock, which is a solution with a known concentration, a very high concentration. We take a little bit of it, like 1 milliliter out with a syringe. We add it to a different flask, and then we add water. Basically, since we're adding water, but the number of moles is staying the same, the volume is increasing, which causes the molarity to decrease. So if we wanted to figure out how the concentration changed, we just use a simple formula. M1V1 equals M2V2, where the M's stand for molarity, the concentration, and V stands for the volume. Be careful, the M does not stand for mass, meters, or moles. It stands for molarity. The 1's refer to the solution you're starting with, usually the stock solution. And the 2 refers to the second solution, what you're going to end up with. So how can we apply that problem? Let's look at number 3. Number 3 asks, how many milliliters of 3.0 molar sulfuric acid, so again, I'm annotating exactly how you should be doing anytime you get a problem like this, are needed to make 450 milliliters of 0.1 molar sulfuric acid. Same thing. So my warning bell to figure this out should be, oh, I have the concentration, two different concentrations but of the same compound. And I'm changing the concentration. I'm diluting it. I'm decreasing it. It's going from 3 down to 0.1. So a dilution formula, M1V1 equals M2V2. Now we just got to plug in our values. Well, the molarity of the stock solution is 3 molar. The volume of the stock solution, I don't know. I'm trying to figure out how much of it I need, how many milliliters. The molarity of the ending solution is 0.1, and the final volume of the new solution is going to be 450 milliliters. Now you might be thinking, Mr. Shar, why didn't you convert to liters? You know, molarity is always with liters. Well, since my unknown, my final answer is going to be in milliliters, and this number was given in milliliters, 450, just to look back up there. Okay. I can just leave that as 450 milliliters, and when I solve for x, my final answer will have the same units. So this is just simple algebra. You solve for x, you get a volume of 15 milliliters. So what this is saying is if you want to take a, think about beaker 1, it has, 3 molar solution in it. How much of it do you have to take out in a syringe to make a final solution, 450 milliliters of it, that has this new concentration of 0.1. Well, you take out 15 milliliters from here, you add a ton of water, how much? Well, exactly 435 milliliters, and that will give you a final concentration that's diluted down to 0.1 molar. Let's look at number 4. Number 4 says, how is the molarity of a 0.5 molar potassium bromide, KBr, bromide, meaning it's an ion, ide, solution changed when water is added to double its volume? Okay, so you might be thinking, oh, I'm changing, I'm going to do a dilution, so I'm going to use M1V1 equals M2V2. True, that might be the old AP chemistry way of thinking about this, but the new way, no calculator, understanding the concept, there's a shortcut. You know the concentration is 0.5, okay? So if the volume gets doubled, well, we know molarity equals moles over volume. So if molarity goes up and it's in the denominator, that means that the concentration, if the volume goes up, it's in the denominator, that means the concentration must get smaller by the same factor. So if the molarity was at 0.5 molar to start, and we've doubled the volume, the new molarity, M2, is going to be half of that, 0.25 molar. That's it. We'll move on, and you'll use this for the stoichiometry titration lab that we'll be doing later this week.